the day. Let me remind you that after this session, this is the last oral session, but this is not the last session. After this session, we have a poster session, which is hosted on Frames, as I have told you. And the poster session is a very important component where our young colleagues are presenting. So please do attend. They will be eager to present their posters. Okay, with this, I will hand over to the chair, Sangeeta Bose, who will be chairing the session today. All right, over to you.
Okay, thank you, Pratap. So welcome to the post-lunch session. So we'll start right away. So let me invite Professor Joy Mitra from IISER Trivandrum. So can you start sharing your screen, Joy?
Yes, thank you, Sangeeta. I'll just share my screen. Yeah.
And he'll be talking. Yeah. So can you go to full screen?
Yeah, that's what I'm doing. One second. Yeah. Can you?
Yeah. So could you just scroll through and just see whether it's yeah, perfect. So Joy will be talking about exploring epsilon near zero properties of conducting oxides. So over to you, Joy. So I'll just send a reminder in 20 minutes so that you have 5 minutes for talk time. So over to you.
Thank you, Sangeeta. Okay, good afternoon, everyone. I thank the organizers for giving me this opportunity to present my work here. So what I am going to be talking about today is titled Exploring Epsilon Near Zero, or ENZ Properties of Conducting Oxides. I am from the School of Physics in IISER at Thiruvananthapuram. And though I am presenting it, the primary part of the work is due to my PhD student, Ben Johns, who will be very soon submitting his thesis. And this is Ben's work, really, supported by other members of the group. Okay, so near zero index media is a very fascinating area to work in, which I kind of didn't go into by design, but stumbled in while working on plasmonics of metals. And in my quest to look for alternative plasmonic materials in the IR or the near IR, that's how I kind of walked into conducting oxides. Now, so what is near zero index media? I'll give a very brief introduction, because even though the properties are very simple and trivial, the consequences are rather fascinating. So what we define in near zero index media are systems where one or more of its constitutive parameters, like the epsilon, the relative permittivity, or the permeability, essentially is very close to zero or is zero. Okay. And typically these materials, I'm going to speak on systems which have the relative permittivity or epsilon of the order of zero, and that's ENZ, epsilon near zero media. But they are typically characterized. They are characterized by the wavelength at which the real part of epsilon actually goes to zero. Now, if the real part of epsilon goes to zero in a lossless media, it is rather easy to comprehend or understand that the refractive index of the material will also approach zero, because n goes as root e, and therefore that would also go to zero. And if the refractive index of a material does go to zero, then what happens? What happens is the wavelength increases. Light can tunnel through deformed waveguides, and you can see a cartoon here from one of the review articles. I have listed quite a few of the review articles which have come out in recent times, and they are all very good, highly recommended. So therefore, what happens as the refractive index goes to zero? You can see the wavelength stretches itself. Light can tunnel through deformed waveguides. There have been reports of giant optical nonlinearities. You can very easily show that the phase velocity diverges, whereas the group velocity practically goes to zero, bringing us to slow light, or light trapped in 3D domains, small but finite domains. you get a large electric field enhancement within the epsilon near zero media, simply because the boundary condition dictates it to be so. So if one of them is a normal media, the other is where the epsilon goes to zero, naturally the corresponding electric field to preserve the boundary condition kind of blows up. And it has very important consequences in perfect absorption, tailoring emissivity, rather a fascinating journey, which we have recently started in the lab. Okay, much of the epsilon near zero research have essentially been in the past on very sophisticated and rather complicated structures like photonic crystals, metal semiconductor waveguides, as you can see, multi-stack layers of dielectrics and metals, metal nanowires stacked and oriented. And it has been rather nice to see all these exotic structures. But nevertheless, since the structures are so exotic, it is difficult to actually realize them, tune them, tailor them under more simpler conditions. As opposed to metamaterials, what has been recently realized is that there is a host of continuous media which actually show epsilon near zero properties. That is, their relative permittivity goes to zero at a certain wavelength. Now, obviously, the most famous example would be all standard metals, and the relative permittivity goes to zero at the plasma frequency if you continue from the Drude model, and you have the ultraviolet transparency at wavelengths below that or frequencies above that. But here you can see there is a whole range of nitrides, hydrides, oxides, and topological insulators, and even polymers, P.PSS, even polymers which has been recently shown to have the epsilon near zero properties, where the epsilon goes to zero at a particular wavelength. Now, it's worth pointing out that aluminum nitride, for example, crosses the zero, the epsilon crosses the zero at 2 wavelengths. And look at the wavelength, it's above 10 microns. Above 10 microns. For vanadium hydride, the zero crossing happens around 500 nanometers. For indium tin oxide and many of these oxides, zinc oxide, cadmium oxide, it happens in the near IR. For silicon dioxide, it happens around 8 microns, and so on and so forth. This is a very interesting view graph which came up in a recent review, Nature Review Materials, and which kind of shows a whole range of materials, oxides, alloys, etc., which display this property of epsilon going to zero at a certain wavelength, and therefore they all harbor the goodies of ENZ materials. Okay. Now, what is worth remembering is that even though the real part of the epsilon goes to zero, the imaginary part of the epsilon in all these materials are not zero; they are finite value. And that's what gives a limiting parameter in actually realizing whatever I spoke about in the first view graph. And typically what we see is that if the imaginary part of epsilon is restricted to around 1 to 2 or below, that is where we actually get the goodies of ENZ materials. Right. Okay. What we are going to talk here today is mainly about indium tin oxide, or the epsilon omega of indium tin oxide thin films. Now, these indium tin oxide is obviously a doped indium oxide doped with tin. The optimal doping happens to be around 10 to 12%. And we have a reasonably large number density. They are transparent conducting oxides. They are transparent in the visible. And you can see here that in the visible, the epsilon is a positive number. And whereas above that, lambda ENZ, it becomes negative. And therefore, it undergoes a dielectric to metal transition, a driven dielectric to metal transition at a particular wavelength, which we call the lambda ENZ. And the value of the lambda ENZ or the ENZ frequency can very easily be tuned. If you look at the Drude model of relative permittivity, it can very easily be tuned by tuning the number density of the electrons in the system and the background permittivity epsilon infinity. And epsilon infinity is more or less a constant. Therefore, by changing the electron density of the system, we can very easily tune. So this is what really fascinated me and people working around me, that you have such a system where if you change the number density, you can tune the ENZ wavelength. But as with realizing many of these exotic properties, bulk of the research actually goes in preparing the right material. How far can you actually control the material and actually get some things done so that it is reproducible, it is stable, it is robust in terms of the results. So, the first part of our exercise was essentially to look at the material aspects of indium tin oxide. But before I go into that, let me again reiterate that for wavelengths above the ENZ, lambda ENZ, it is a metal, it's optically a metal, and therefore it supports surface plasmons and is plasmonically active. Below the lambda ENZ, it is optically a dielectric with the real part of the permittivity being positive. Okay, and being positive. And what is seen here is that if you look at the refractive index, there is a very interesting regime in the center. And this interesting regime in the center, which is colored in green, essentially shows a regime where the permittivity is actually positive. The real part of the permittivity is actually positive, but the refractive index of the material is less than 1. Which is less than the refractive index of vacuum or air or free space. So this is the green region, is perhaps the most interesting region that we are exploring now. As I said before, we entered these systems to explore the plasmonically active domain, which is the metallic domain. But now we are slowly transitioning into this narrow region, which is of the order of 200 nanometers in width, and which lies just below the lambda ENZ. So this unique combination of the refractive index being positive, the permittivity being positive and the refractive index being less than 1 in that wavelength regime allows propagation in a media with refractive index below 1. And let's see what happens then. Okay. Now, so the first part was obviously to try to tune the lambda ENZ and how robustly we can do that. Now, if you look back in literature for many of these systems, we realize that the dopants are essentially the ionized tin states. This is the band diagram of ITO, and as you go on doping with tin, it creates these dopant states that donates the electrons to the conduction band, with the Fermi level now lying firmly within the conduction band, and that's what makes it a conductor or a transparent conducting oxide. So how do we control the number density? Now, the easiest way of controlling the number density is to actually tune the tin oxidation ratio. Now, the tin actually exists in two oxidized states, tin 4+ and 2+. And if you manage to change the oxidation state of tin, you manage to control or change the number density in the system. And after a bit of survey and a bit of initial work, we realized that we can actually do that by controlling the oxygen vacancies in the system. So if you have large number of oxygen vacancies in the system, you have a very large tin 4+ to 2+ ratio. A low oxygen vacancy gives us a low 4+ to 2+ ratio, which essentially means the conductivity is going to decrease. Okay. So once we realize this, that this is going to happen, we started off looking very carefully at the tin ratio with a XPS spectroscopy, and of an optimally doped indium tin oxide. So here, the first graph here actually gives you the peak for SN2+, SN4+, and then gives you the oxygen peak here and another oxygen peak here. Now, these two oxygen peaks actually originate from very different sources. This is oxygen in a stoichiometrically pure region, whereas this is oxygen in a oxygen deficient region. So therefore, if I tune the ratio of these two peaks, notionally what we expected was that these two will also change. And let's see if that happened. And we went ahead and started annealing the system under various conditions. Now, what are the annealing conditions? The annealing condition were either in oxygen-rich atmosphere or oxygen-lean atmosphere with temperature and time as parameters. Okay, so we'll have to obviously estimate the lambda ENZ, which we mostly did from angle and wavelength dependent reflectivity measurements. A typical measurement is shown here, and from which we calculate, back calculate for the ITO coated glass stack, we back calculate the relative permittivity. So we take the experimental data, fit it, and then calculate the relative permittivity. And for this sample, as you can see, the epsilon goes to 0 at around 1280 nanometers. Now, since it's a conducting material, we knew that we could easily check whether properties are changing or number density is changing by looking at the resistance of these films. And what we saw was that if we anneal it in air, which is oxygen rich, for typically 10 minutes at various temperatures, we saw that beyond 350 to 400 degrees centigrade, the film was becoming resistive, showing that most likely the number density was decreasing. So once we realized this, we went ahead and then optimized annealing in oxygen as a function of time and temperature. And after a few months of detailed work, we figured out that if we do the annealing at 350 degrees centigrade in air, the oxygen vacancies are quenched, decreases, and the film becomes more and more resistive. We did the optical measurements and calculated the lambda ENZ or lambda ZE. And what we saw was that it was absolutely reproducible. The change in the number density and the change in consequently the lambda ENZ was absolutely reproducible up to plus minus 10 nanometers. Reproducibility at higher temperatures was a bit more erratic, and therefore we stuck for the rest of our work to annealing at 350 degrees. Not only did the films become more resistive as we annealed it in oxygen, it was also reversible. If you then annealed the film subsequently in vacuum, what we saw was that oxygen was going out of the system and oxygen vacancies were being created, and the film again became more and more conducting, as well as consequently the lambda ENZ went on decreasing. Another important parameter, as I have been mentioning before, is the imaginary component of the permittivity, which is characterized by the scattering. And our endeavor was to actually see that the scattering coefficient does not really increase. And that's how the scattering coefficient behaves. It's more or less, it kind of decreases by 50% and kind of regains the value, and so on and so forth. A detailed XPS study followed, which actually showed that indeed, as we were going across the samples with quenching the oxygen vacancies, the tin ratio was actually decreasing. And you can see the tin 4+ to 2+ ratio was actually decreasing. And consequently, the electron density, which is these triangles here, was also decreasing across the samples. And the story kind of made sense. It was extremely reproducible and robust. We went ahead and once establishing the protocol, and we went ahead and tried to make samples, as many samples as we can, showing control. And this is a range of selected samples from our many tries, which actually shows that, you see, we can actually tune the lambda ENZ right across from 1280 nanometers to around 2800 nanometers. This is the limit of our optical detection system that we developed in the lab in the near IR regime. And correspondingly, the number density actually changes from by an order in magnitude, 10 to the 21 to 10 to the power of 20. But as I repeatedly said, that please remember that there is this small region here, approximately 200 nanometer, 2 to 300 nanometer below the lambda ENZ, where the refractive index is below 1, as well as the relative permittivity is actually positive. Okay. So this is that delta lambda region. And as you can see, that delta lambda region is typically 200 to 300 nanometer, where we can play these tricks. And these are the refractive indices at lambda ENZ, the corresponding lambda ENZ. And you can see that the refractive indices are typically around 0.4 and so on and so forth. Yeah. Okay. So what do you do with it? Okay, so what we first went on to, since we entered the field in terms of plasmonics, trying to discuss optical surface plasmons being excited in these oxide films in the near IR regime. The first thing which we did was we went ahead and took a film, 120 nanometer film of ITO, and we said that let's try to excite the plasmons at wavelengths beyond lambda ENZ, where it is optically a metal. And indeed, these are kind of ATR absorption spectra in the ATR mode, excited through a prism. And experimentally, what we saw was that, yes, indeed, you have large absorption, which pretty much matches the simulated plasmonic response of these 120 nanometer thin films. But what was even more surprising to us was that if we decrease the thickness of the film, if we take the same game tuned films, which were much, much thinner, 20 nanometers, thin films, then the plasmon spectra was, absorption spectra was essentially very, very different. Instead of having this asymptotic behavior, experimentally what we saw was that the absorption band was straddling the lambda ENZ wavelength. And when
you have 5 minutes per speak time, talk time.
Yeah, and when we actually did the simulations, indeed that turned out to be so. And so we were rather intrigued that where does this come from? And then we kind of figured out that in 2015 there had been some initial studies which said that if you actually decrease the film thickness, the plasmon dispersion relation, this is the bulk plasmon dispersion relation, this solid curve here. If you decrease the film thickness, it actually becomes almost flat, dispersionless, very close to the light line. And not only that, to the right of the light line, you have this plasmon mode, and to the left of the light line, we get radiative modes called the Raman mode, which we will also discuss in a few minutes. Okay, so one important part was that for these very thin films, the plasmons will be excited, but exactly at the lambda ENZ. So if you change the lambda ENZ, then the plasmon modes will also change, and they will be practically dispersionless. They are absolutely flat, and which is what we were seeing here for a particular film, which had a lambda ENZ of 1280. So we said that, okay, fine. So it's very easy to check now. Let's check for the other films. And indeed, when we actually tuned the lambda ENZ of films up from 1260 to 1380 to 1650, we saw that the plasmon mode in the thinnest of the films, 20 nanometer films, was essentially shifting. So again, we couldn't resolve this fully because this is the limit of our detector and the setup. Right. So where does that leave us? Okay, so it is doing all these things. So how useful is it in actually any practical applications, or what is the resale value of this understanding? Now, the resale value of this understanding comes from the fact that plasmons cannot be excited in metals directly from air simply because of the wave vector mismatch. But now what happens due to this Brewster or Raman mode existing on the left of the light line, and the fact that the refractive index of the material is actually less than 1, it is possible to excite these modes from air. Okay, so we can excite these Raman modes from air directly onto these material. Not only that, if you actually look at the electric field, this is the calculated electric field. If you look at the calculated electric field, you see the electric field is highly enhanced and trapped within that ENZ material thickness. And therefore, it allows for high power dissipation, because power dissipation goes as epsilon double prime times E square. Epsilon double prime is small, but E square more than makes up for it. That very large enhancement in electric field locally absolutely makes up for the deficiency in epsilon double prime. So even though the films are not very lossy, we actually get a very large power dissipation. Where is it useful? It is useful in directional and spectrally selective perfect absorption. So we were in the process of, and this is kind of the pre-pandemic we kind of were wrapping these things up and then trying to prepare these materials. But unfortunately, we couldn't go too much into preparing these materials and stacks. Meanwhile, in 2021, again, a science paper has come out, which exactly exploits the same idea. It has these oxides. It has this stack of oxides, 3 stacks of oxides, and essentially proposes directional control of broadband thermal emission. We though have theoretically investigated perfect absorption on highly reflecting materials, and also to some extent omnidirectional spectrally selective reflectivity. For this part of the work, we chose another material, which is cadmium oxide in the same class, cadmium oxide on gold. And what we see is, if you look at the reflectance map of these very thin coatings, what we see is there are regions of very high absorption, very low reflectivity, even for films as thin as 20 nanometers, 50 nanometers, 100 nanometers to 400 nanometers. Remember, we are doing this in a wavelength range of something like 1500 nanometers, and these are way below the lambda by 4 limit. Now, so there is a complicated, not really complicated, but there is a detailed understanding which we have in our publication of why these things actually happen. But within this region, wavelength range, where lambda n is equal to 1 and epsilon goes to 0, this delta lambda, we see these strange properties. To cut a long story short, what we actually see is that as a function of wavelength, the direction of maximal emission changes with thickness. So we kind of can establish that the thickness is a very easy control parameter to do the thin film coatings. If you change the thin film coatings, immediately they start emitting in various different directions. Okay, and this is the dispersion plot. I'm not going into the details of it, but what we can see is that we have these points here which shows perfect absorption, and it is easily tunable by 2 parameters, either the loss in the system by epsilon double prime affecting epsilon double prime, or by changing the thickness of the thin films themselves. And ultimately, to show that indeed, the ENZ film is doing the trick of perfect absorption, where does the energy go? There is zero reflectivity. The energy is completely eaten up by the structure. We show here a calculation of air ENZ gold. Okay, and this is done at around 1890 nanometers. So gold is highly reflecting, and you have a thin film of ENZ, which is just 20 nanometers in thickness. And what we see is that the electric field is highly enhanced. If you do the power calculation, we see that less than 4% of the power is dissipated in gold. Less than 4% is dissipated in gold at perfect absorption. The rest of the 96% of the power is actually absorbed by this very thin ENZ material. Okay, and that is a real selling point of this story. In terms of, I'll just end with spectrally selective absorber. So you have directionality. What about spectral selectivity? And here we have the reflectance spectra of a structured oxide film on stainless steel with a coating thickness of 150 nanometers. And you can see the reflectance spectra of this structure. In spite of just 150 nanometer of oxide films, carefully tuned oxide films, what we see is that the reflectance is around 10% on an average in the entire visible, and then suddenly goes up to 80% above a critical turn-on wavelength. And these are absolutely tunable by tuning the lambda ENZ, the thickness of the films, and so on. Most of our work have been, these are the publications, the first 2. The third one is a much more detailed analysis, which we have currently on archive. So I suppose time is up, and it's acknowledgements. These are my students. Ben is there, who did most of the work, and assisted by Hari to a very large extent, and others. Currently, the work is being carried on by Arun, Shravani, and Shashwata. Ben is about to submit his thesis. He's just finishing up his thesis. And and all my funding agencies over the years who have enabled this work. Thank you so much.
Thank you, Joy, for a wonderful lecture. So the forum, we can just probably take one short question because you run out of time. Questions? Okay, maybe I can just ask one short question. Sure. So you saw, so since your lambda ENZ is so much dependent on the electron density, yeah. So I would assume that with thickness also your density would change, right? So why in your ITO, why doesn't the lambda ENZ not change?
Why should the number density change with thickness?
I mean, that's what you showed in your later half also, or did I miss something? In your next system which you showed?
Yes. Well, the cadmium oxide has a very different, so we chose cadmium oxide simply because it has a much lower epsilon double prime. Okay, it has a much lower epsilon double prime. Actually, the number density is also low because the lambda ENZ is also more redshifted. But the primary advantage which comes across these materials is how far we can tune not only the epsilon prime, but the epsilon double prime, which is the loss in the system. Mm-hmm. Okay, yeah. So no, the number density is not a very strong function of at least within the range.
But that's your tuning with the oxygen vacancies, right? So yes, if that would change with thickness, right? I would assume during.
Well, that's what I'm about to say. That see, these are not bulk films. All these films are below of the order of 100 nanometer and below. Okay, so while I haven't done a depth profiling, okay, we have done it on various thin films like 20 nanometer, 50 nanometer. 70 and 100, 120. Okay, and what we saw was that the number density calculations from the optical measurements, also we did Hall measurement. Okay, they kind of follow each other and they are extremely robust. So we are in fact looking for in a thicker films graded number density changing. That can we actually do that? And if we can do graded number density changing reproducibly, that is like a stack of different lambda ENZs. Okay, but as of now, even on thicker films, our initial results are not very promising. We are trying to do it. That can we actually engineer graded lambda ENZ?
Okay. Yeah. Okay, thank you very much. So let's thank once again Professor Mitra for an excellent talk and move on to.
Yeah, just hold on.
Sangeeta, you are muted.
Okay, so let's move to the next talk. Let me invite Ashish from IISER Pune. So he'll be talking about exotic states of charged excitons in 2D semiconductors. So over to you, Ashish.
Thank you, Sangeeta, for your kind introduction. Yes, I have very recently joined IISER Pune as an assistant professor. So much of the work which I am going to show today, this is done in University of Münster, where I was a junior group leader for about 6 years or so. We collaborated with National High Magnetic Field Laboratory in Grenoble and also with the University of Warsaw in Poland and also with the Technical University in Denmark. So I will be talking about some exotic states of 3-particle Coulomb-bound composites in 2-dimensional semiconductors, and I will be explaining these terms as I progress. So my area of research mostly deals with investigating these quasi-particles, which are these Coulomb-bound quasi-particles such as excitons, trions, pi excitons, and charged pi excitons in 2-dimensional materials under magnetic fields. For example, we study Zeeman effects, valley polarization and coherence effects, Landau quantization and diamagnetic shift, and so on. I have summarized this area of research in this recent invited perspective in Journal of Applied Physics, which says magneto-optics of layered 2-dimensional semiconductors and heterostructures, progress and prospects. So the interested audiences can refer to this article for this. However, today's talk does not deal with magnetic fields. It deals with these exotic states, these 3-particle states called trions in 2-dimensional semiconductors, such as tungsten disulfide as an example. So in the first work, I will talk about excited states of trions where the two electrons are in the 2s shell of the hole here. And we talk about bound and scattering states. And the second work, I talk about dark states of these trions, which do not interact with light. However, we see their effects on the luminescence and their absorption spectra. We find the energies of these dark trions by looking at their effects on these spectra. And we also try to tell if tungsten and molybdenum-based materials are bright or dark. And I will tell what this means. So let's start with some basics first. When we shine some photon on a semiconductor, we create electron-hole pair, and these electron-hole pairs are bound by Coulomb interaction, and this entity called exciton is created. This exciton absorbs strongly below the band gap by an amount equal to binding energy. So the binding energy is given by the single particle band gap minus the optical band gap, or the point energy at which the excitonic transition is taking place. And this exciton can recombine again and give rise to emission called excitonic emission. In three-dimensional semiconductors, such as that of a three-dimensional gallium arsenide or silicon, the binding energies of these excitons can vary from a few milli-electron volt to few tens of milli-electron volt. Now, when we compare it with room temperature, which is of the order of 26 milli-electron volt, this is small. So therefore, three-dimensional excitons are not very stable at like elevated temperatures or room temperatures. However, theoretically, if we create a two-dimensional semiconductor, then the binding energy of this exciton can be 4 times than that of the 3D exciton. So therefore, it is more stable. So this is one of the reasons why two-dimensional excitons are, just a second, are promising platforms for studying this semiconductor physics at elevated temperatures. Now, we will be talking about optics, and excitons strongly modify the absorption spectrum. Let's look into some basics of this. Let's suppose I shine a photon in a quantum well where there is a semiconductor such as gallium arsenide is sandwiched between two barrier layers of aluminum gallium arsenide, and then the electron and hole levels are quantized, and then we can have optical transitions. Now, an exciton is created. This will be a two-dimensional exciton. What we expect is that this exciton will appear as a strong resonance just below the band gap by an amount equal to binding energy in the absorption spectrum. Okay, but this is a ground state exciton. Now, exciton is a hydrogen atom-like species, so it also would have some excited states, yeah, 1s, 2s, 3s, 4s, and so on. And then there is also a continuum. So a continuum is where an electron and hole can have scattering states. The electron scatters off from a hole, but still there is Coulomb interaction between them. So if we zoom into this region here, then we find that, so now this is expected spectrum, this is not experiment so far. Then we find that there should be some 2s state, some 3s state, and so on, but they continuously reduce in intensity. So they are very tough to see, and also they are very close to the band edge or the single particle band gap EB. Therefore, the line width has to be very narrow and the sample quality has to be excellent to be able to see these see these excited states of excitons. So what we expect is this excited states of excitons, and also we also see expect a two-dimensional step-like feature, because now this is a two-dimensional semiconductor. So you expect a two-dimensional density of states contribution to the absorption spectrum, but this is enhanced due to this Coulomb scattering, and this effect is called Sommerfeld enhancement. But the point is that in the real spectrum, this is expected to decay a bit, to reduce a bit from the band edge due to this Sommerfeld enhancement factor. Now let us look at the experiment. So we have this quantum well where there are two types of transitions, two types of holes actually, called heavy hole and light holes, due to hybridization of orbitals, p orbitals in the valence band. So there are two types of excitons called heavy hole and light hole excitons, and they appear as strong resonances now in the absorption spectrum. Now this is experiment, and then there are these step-like features which are superimposed on the top of each other, one due to heavy hole and one due to light hole, and then they contribute to the absorption spectrum with the Sommerfeld enhanced 2D step-like feature. However, we notice that there should be excited states of these excitons which are not visible here, because the binding energy is of the order of 10 MeV, whereas the line width already is of the order of 5 MeV. So the excited states of excitons here are merging. So it's very tough to see these excited states in quantum wells. You need very high quality samples in quantum wells. So with this message, let's go towards now trions. Now we look at these excitons first. There are these ground and excited states of excitons and scattering states. If we add one more electron in, in this orbit of this exciton, then we get a trion. And this trion now starts to absorb below the exciton by an amount equal to trion's binding energy. So these trions were first observed in doped cadmium telluride single quantum wells and in absorption and in photoluminescence around 1990s. And the binding energy is very little. It's of the order of 1 to 3 MeV. So these experiments are done at very low temperatures. For example, here it's 1.7 Kelvin temperature. However, we can also put an electron along with this 2s shell, and then we can have a doubly excited trion where both electrons are in the outermost shell. Now, these excited states of trions have not been detected so far before this work. Similarly, there can be excited states of the trions, scattering states of the trions where the electron can scatter from an exciton. These scattering states have been predicted theoretically in 2001. However, they have not been experimentally observed in quantum wells. So this is the reason we move to two-dimensional materials with the field started with 2004 with graphene. However, graphene has no band gap. However, in 2010, MOS2 was exfoliated, which has a band gap, which is a semiconductor. It's much thinner than quantum wells. Therefore, it's an ideal two-dimensional material. After that, there is a zoo of two-dimensional materials. We will focus on these transition metal dichalcogenides such as MOS2, MOSE2, WS2, WSE2, and so on in this work. The point is that in these TMDCs on transition metal dichalcogenides, the binding energy of excitons is very large. It's an order of magnitude larger compared to the 3-5 semiconductors. And the excitons appear as a strong resonance in the absorption spectrum. For example, this is a tungsten disulfide, a monolayer tungsten disulfide layer. And here this orange is the absorption spectrum of an exciton. If we add an extra electron, we get a trion, and we find that the binding energy of trions is also much larger, an order of magnitude larger compared to the 3-5 semiconductors. Therefore, we should be able to see these trions at elevated temperatures now. Now, these trions also appear strong in the absorption and in luminescence spectra below the exciton by an amount equal to the binding energy of the trion. So here, orange is the absorption and blue is the photoluminescence spectrum of tungsten disulfide film at low temperature at around 10 Kelvin in this work. Let us come to the first part of the work where we'll be discussing now excited states of trions in this monolayer of tungsten disulfide. There is a slight story behind this. We know that the Rydberg series of hydrogen atom is well known. Yeah. However, if we create an H negative ion, it's found both theoretically and experimentally in the atomic physics that its ground state is stable and it appears below 1s state. However, if we add another electron in the 2s level, 2s shell of the hydrogen atom, such an H negative ion is unstable. Yeah. So such an H negative ion, which should appear somewhere here, is unstable. So it does not appear. Both theoretically and experimentally it has been seen. However, if you add both electrons in the 2s shell, such an H negative excited state is stable and it appears just below the 2s state. Now we wanted to see if such a thing is possible to observe in the solids as well. So we try to find these in monolayer transition metal dichalcogenide. We choose tungsten disulfide, which is encapsulated between thin layers of hexagonal boron nitride, which is an insulator. This is our sample structure where hexagonal boron nitride is encapsulating a monolayer of tungsten disulfide, and we measure its absorption spectrum by measuring reflectance and transmission in the same conditions. And this is the absorption spectrum. You see some features here, some resonances which correspond to 3 types of excitons. We only focus on this region of the spectrum. Let's zoom into this region, which is essentially ground state A exciton. It's called the A exciton. Now we have this feature, a strong feature corresponding to this 1s or the ground state of A exciton, and we have 2 features which correspond to the trions. Well, let's zoom further. There are some more wiggles here. So we zoom further and we see that there are more features here. There are some step-like functions also appearing, just like in quantum wells. So let's try to see what these are. So we model this spectrum by standard bound states and scattering states formula. And we find that we can fit this spectrum nicely by these step functions as well as these Lorentzians. So these two, of course, we discussed. These are these ground state trions, just like this, which is shown in the left side. This is the ground state of exciton here. And then there is an excited state of exciton, which was also well known by this work, that the excited states of excitons are visible in these materials. This such as the 2s state, this 2s state of exciton. However, what's new is that we start to see now this step-like thing. So these are excited scattering exciton scattering states, which were not visible, which were not seen before our work, because mostly people focused on reflectance spectroscopy, but one has to do careful absorption spectroscopy to start seeing these. And also there are further things. For example, there is this extra peak visible, which we tentatively assign to a 2s trion or this excited state trion. So this is also new. And then we have these trions scattering states, which are also step-like function, which appears just after the exciton, the neutral exciton. These are trion scattering state, which should appear just after the neutral exciton. However, these are tentative assignments, and we'll have to do more to know if what we have assigned is correct or not. So let's proceed. First, we go to our statistician partners, and they do GW-BSC calculations. They calculate the absorption spectra and find the probability distributions of various features which they calculate in the absorption spectra. Now, this is experiment and this is theory. And in theory, they also find that there has to be two types of trions, or the ground states of trions, and one exciton, which agrees well with our experiment, and the probability distribution should be spherical without any node or anything. So this is hydrogen-like 1s state. Now, when they look into the excited states, what they find is that similar to us, they have excited state of trion here and an excited state of exciton, which has a wave function similar to the probability distribution function, similar to a 2s state of hydrogen atom. Of course, but this is not enough because we are experimentalists. We would do more. So then we try to see if what we are seeing in our experiments are actually 2s excited states of trions or not. For that, what we use is something well known from literature. In literature, it's known that if you have an exciton trion pair, such as here, an exciton and trion, and if you raise temperature, then what happens is the exciton starts to gain its strength and trion starts to lose its strength with raising temperature. So if this happens, this is called transfer of oscillator strength. And if this happens, that means you have an exciton trion pair which is connected with each other. To understand why this happens is the following. For creation of a trion, we need excess electrons. So we need a doped semiconductor, right? So we have this valence band and a conduction band, and then there are some excess carriers which are represented by this yellow, this orange line in this band diagram. Now, for creation of a trion, you need extra carriers here in the center of the band where the optical transition takes place. So now if we are at low temperatures, we have some Fermi-Dirac distribution of these carriers, and many carriers are available for creation of trions. So you can easily create many trions. However, many of the states here are already filled up now due to the extra electrons. So you are not able to create the excitons very efficiently, because for creation of an exciton, you have to excite an electron from the valence band to conduction band. Now, if everything is already filled there, you will not be able to excite there. Therefore, you will not be able to efficiently create the excitons. Therefore, the oscillator strength of exciton at low temperature is low, whereas for trion, it's high. Now, when you raise temperature, you have a Fermi-Dirac redistribution of carriers, where the carriers redistribute to higher energies or higher momentum states. Then at the center of the band where the optical transition takes place, the probability of creation of trions goes down because now the number of available excess carriers is less. However, the probability of creation of neutral excitons increases because you have now empty states and you can excite very large number of electrons here and can create electron hole pairs now. Therefore, the oscillator strength of trion goes down, whereas that of exciton rises. Now, we test it first if it's true in our two-dimensional materials just for ground state trions. Then we go to the excited states. Now, here are the ground state trions, these two features, and there is this ground state exciton. When we raise temperature, this is absorption. When we raise temperature, we see that these ground state trions, they lose oscillator strength. Whereas in exciton, if we calculate the area under the curve, which is the measure of oscillator strength, it rises. So what we see is the integrated absorption for the ground state excitons rises as a function of temperature, whereas for the trions, it goes down. Now let's see if this also fits, this transfer of oscillator strength also fits for the case of, for our case of 2s states. So we have this 2s trion and 2s exciton, and what we notice is the same, that when we raise temperature, 2s trion loses strength, whereas 2s exciton gains. So 2s trion loses and 2s exciton gains, trion loses. So similar to 1s states, 2s states also show transfer of oscillator strength, which is another piece of evidence that what we are seeing here is a connected set of excited states of trion and exciton. Now, one further piece of evidence is the following, and it's very nice, that when you have a trion state appearing below an exciton state, then an exciton can scatter back to this trion state by capturing an extra electron. Therefore, the line width of this exciton is rather large because there is a contribution, the scattering contribution from one state to the other. However, if this trion state vanishes for some reason, then this scattering channel won't be available. So in that case, the line width should become smaller because there is no scattering, there is less scattering happening of this exciton state to some other states. Now, this is what we see exactly. For the trion, the line width keeps on increasing. However, for the neutral exciton, excited exciton, it goes down actually when we raise the temperature. Now, in semiconductor physics, this is not very common. When we raise temperature, the line width goes down. But here, this is a piece of evidence that these two things are connected with each other or coupled with each other, and one of them is a trion and one of them is an exciton. Therefore, in conclusion, we have found an excited state, excited bound state of a trion here, and we also found evidence of scattering states of trions and excitons. We also find that these three particle state, they govern a wide spectral energy range. For example, we have these excited states of trions, and we also have this continuum of the trions, which runs throughout the spectrum, which was not seen earlier. For more details, you can refer to this work. Now, let me go to the next part where we start discussing about the dark.
Ashish, you have 5 minutes of talk time.
Thanks, Sangeeta. I will be finished by then. So we are going to discuss about dark trions now, which do not interact with light. Let us take a look at the band structure of tungsten disulfide or tungsten diselenide or molybdenum disulfide first. And in this case, what has been realized or what has been agreed upon by the community at the moment is that conduction band is split due to spin orbit splitting, and the bottom of the conduction band has an opposite spin than the top of the valence band. Then if you create an exciton here, this exciton is a dark exciton because this does not couple with the photon. For it to be able to couple to the photon, you should have same spin because the spin has to be conserved. Therefore, this is a dark exciton. Now, this is a low energy state. Now, if low energy state in a crystal is dark, that means it will not be a good emitter of light because the emission comes from low energy states, right? So therefore, it's very important to understand if there are low energy dark states inside material or not. For MOSE2 and MOTE2, what's found is that the lower energy conduction band has same spin as that of the top of the valence band. And then you create a bright exciton. So lowest energy state in MOSE2 and MOTE2 is bright. So this was found in 2015 by us. Now, if we make trions, if we create trions, the band structure is a little bit complicated because now you have three particles and two types of valleys. One is K valley and one is K prime valley. Let's suppose we have tungsten disulfide and we create an exciton, a bright exciton, by putting a hole in this and an electron in the top band, which is a bright band. Then we can put an extra electron either in this band or in this band. So we can have two types of bright trions. I will not go into details because this is a bit involved. However, we can create another type of trion where this hole is of the opposite spin than the electron. Then you can have another electron here in the other valley, and this trion is a dark trion because the exciton here is dark. The exciton decides the selection rules. Now, this would be the lowest energy state, and this should, contain most of the carriers at low temperature. So therefore, it's very important to understand if these dark trions exist, and if they do, what are their energies in these materials. Now, they do not interact with light, and they are very difficult to probe optically, where there are only few works so far. So in this work, we see the effect of dark trions on absorption and luminescence, and we try to find which materials are bright and which are dark. So what we do is we study the photoluminescence with temperature. Earlier, we studied absorption with temperature on monolayer tungsten disulfide. Let's suppose there are two types of bright trions, and let's suppose there is a dark trion state. slightly below in energy than this bright trions, then a creation of population of trions in such a system will have a Fermi-Dirac redistribution because trion is a fermion. Then most of the trions at low temperatures will be occupied by the dark state, and the bright states will emit a little light, very little light. But when we raise temperature, the light should increase, the emission should increase from the material, because you are redistributing these trions to the higher energy, which are bright states. So then the intensity of the bright trions can be written as the number density of bright trions multiplied by the oscillator strength of these trions. Let us see what happens in experiment. So we have these two trions, and we raise the temperature. We find that the trion intensity is increasing by raising temperature, and then it starts to reduce. So these are the only trions on which we are focusing. We are not focusing on the other features. So let's plot the integrated intensities. We find that the intensity first increases and then decreases for both of these trions. Now we had expected that the intensity should increase, but why does it decrease? Well, there is this other term, oscillator strength, which we already calculated, actually, which we already measured in the absorption spectrum, which I showed you in previous part of the talk when we discussed this picture. And this oscillator strength goes down very fast as a function of temperature. And then we can fit with this oscillator strength function, these two curves, and they fit very well with when we have this energy of, when we can assume that there is a dark state of trion 19 MeV below the bright state. Therefore, in tungsten disulfide monolayer, the dark trion is the lowest energy state by 19 MeV, which is what gives rise to this integrated photoluminescence behavior. In fact, then this was confirmed very recently in another work by a direct measurement of dark trion energy by some other method, by some magneto-optical techniques. So then we do this analysis on other materials, and in tungsten diselenide, we find that again, similar to disulfide, we have the dark trion, which is the lowest in energy by 19 MeV. For MOSE2, the lowest ground state is actually a bright state by 6 MeV. The dark state is 6 MeV above the bright state, whereas in MOS2, the dark and bright states almost coincide in energy within 2 MeV. Therefore, in conclusion, we find that a Fermi-Dirac distribution of the combined population of dark and bright exciton governs the photoluminescence and absorption of 2D materials. Tungsten-based materials are dark by 19 MeV. MO-based materials are bright, or MOS2 is actually a mixed state. In summary, we have discussed that there are excited states of trions and also scattering states of trions in doped two-dimensional absorption spectra. And then we discussed that absorption and emission is described by the Fermi-Dirac redistribution of trions in doped semiconductors. And we determine the dark trion energy, where we find that tungsten-based materials are dark, MOSE2 is bright, and MOS2 has a mixed state. I would like to acknowledge our collaborators for experiments from University of Münster and theory from University of Münster and DTU, and also collaborators from Grenoble and Warsaw. Thank you.
Thank you, Ashish, for an excellent talk. I mean, it's one of these experiments where you want to see something and you've seen it. I mean, really great.
Thanks, Anita.
Yeah. So the forum is open for questions, comments.
I raised
Hello, sir.
Yeah.
Hello,
Please
Debjan.
go ahead. Yeah.
Hi, Ashish. It was a very intriguing talk.
Thanks.
And just wanted to know one thing, that in trion, whenever you tell about trion, there are another kind of charged quasi-particle, which is 2 hole and one electron. So usually those quasi-particles are never kind of pointed out in the experiments and all those things. Usually that negative trions are always getting the whole focus.
Correct.
And the positive trions are usually neglected.
Yes.
Is it because of the fact that the system is less hole doped, and that's why you are...
So most of the materials from whichever sources we find, the materials are unintentionally n-doped. That's what we find always. But if we apply gate voltage and if we on purpose charge these materials on positive or negative sign, we can switch from positive trions to negative trions. We have seen this very recently in our experiments as well.
So will it be possible to extract some similar kind of excitation spectra for positive trions too?
Yes. So we see that there is only one kind of positive trions which which contributes to the absorption and luminescence spectrum. Here we see two types of negative one, but positive is only one type. That's what
only one is. Only one is.
Yeah, no. I mean, only one type. Like there are two types of these negative trions here.
Yeah, that's what you are having. One is and one
Exactly.
2 is. So positive trion, you are having only one is, not 2 is, right?
No. Yes.
Okay. Thank you so
Thanks,
much.
Devda.
Yeah, Shravani, you've got a question. Please go ahead. Unmute yourself.
Yes, sir. Hello.
Hello, Shabani.
So I wanted to ask you something. You have modeled WH to monolayer, right? Using some modeling technique for the absorption spectrum of that.
Yes.
Yes, sir, can you please elaborate a bit on that? You showed some equations. So I was asking, I was wondering, what method do you use, like any FTDT method or something for simulating that?
So what kind of equation? So we have either by modeling, we have modeled either the spectra, or we have modeled, or there is some modeling involved here. Now this is an ab initio theory, which is done by my colleagues. And then there is another type of modeling involved in this work, which is here, which is the Furby-Dirac equation, essentially, multiplied by the oscillator strengths.
Yes, sir. I was asking about that absorption spectrum. So that I wanted to ask, like modeling, like this finite domain, finite time domain modeling, something like that, or
you mean this one, these ones here?
Yes, absorption spectra.
So these are done by my colleagues. I am not an expert, but what I can tell you is these are some kind of DFT, density functional theory calculations with, on the top there is free energy term, free energy corrections, GW corrections, and then you solve Bethe-Salpeter equation for introducing the Coulomb effects to calculate the absorption spectra of excitons.
Okay. Thank you, sir. Yeah. Okay.
So I think we'll wrap up the question answer session. So thanks once again, Ashish, for an excellent talk.
Thanks, Anita.
So we'll move on. So let me invite Professor Kaushik Majumdar from IISC, and he'll be talking about observing perfect valley coherence in monolayer semiconductors. So Kaushik?
Yes.
Could you go to full screen, please?
Yeah, I'm trying to. Yeah, is this full screen now?
Yeah, perfect. So, so I'll give a warning in 20 minutes.
Sure, thanks. So I thank the organizers for inviting me to deliver this talk. So I'll be talking about observing this perfect valley coherence in monolayer semiconductors. So this is a work which has been done by my student Garima Gupta, which goes in her thesis. We also thank Kenji and Takashi for providing us the AGN flags. And I also thank DST, MHRD, and ISRO for funding. So Ashish has done a great job in introducing several concepts of excitons in 2D materials. So with that background, so I will directly go into the origin of valley coherence. What do you mean by valley coherence in this monolayer semiconductors? And then, so we'll talk about, how do you observe the sort of perfect valley coherence? So there are two aspects. One is the generation part, where you have to generate good states, and also how do you retain these good states, which is sort of more difficult task. So these are the primary thing I'll be focusing in the talk. And then to the end, if time permits, I'll sort of try to combine these two, and so that it's possible to generate ultra narrow, highly polarized emission from these monolayers. All right. So let's first see, what do we mean by this valley coherence in monolayer TMDs. So in TMDs, the monolayer semiconductors, so we break the inversion symmetry, and we have a chiral light matter interaction. So in particular, in the Balois zone, you have this n equivalent K and K prime values. So in particularly, so this because you have to sort of conserve the angular momentum in any process. So in the K value, for example, let's say is it absorbs sigma minus this polarized light, then the K prime would be sort of absorbing sigma plus polarized light. So this side of left hand side, right circularly polarized light can be absorbed by two different valleys in these monolayers. Now, let's say you are exciting with a linearly polarized light, which you can think about like a coherence to the position of sigma plus and sigma minus. Then you can sort of generate a coherent state of these K and K prime values. However, the unfortunate part is that such valley coherence which you can generate, but then it quickly degrades. So the question is, how can you increase the length of this time by which this coherence is maintained? So that's the focus of this talk. Okay. So just to give some preliminary basics, so this is sort of the density matrix formalism of this polarization, where let's say we are talking about a circularly polarized light. So psi is sort of an arbitrary state in this block sphere. And so if you want to find out the DOCP, so we call it the degree of circular polarization. So this is a term that I'll be using on and off in this talk. Degree of circular polarization sort of tells you, so this is sort of the, suppose you are exciting the system with a sigma plus circularly polarized light, and so you are measuring in co and cross polarization, meaning your analyzer is either sigma plus or sigma minus, and you find out the I1 minus I2 by I1 plus I2. So this you can mathematically so easy that it's really the coefficient of this sigma z. Right. So the DOCP directly corresponds to the valley polarization of the system. On the other hand, if I excite with linearly polarized light, so I can write down it in the basis state of, let's say the X, the linearly polarized states, then I can find out the degree of linear polarization. So that directly corresponds to the degree of valley coherence. Okay. So with that in background, so if we try to measure, let's say, this kind of cross and co-polarized valley polarization and linear polarization, in both cases, you see the typical numbers we see are fairly low, like this is like 11% and this is like 37%. Okay, so there's a reason why linear polarization or the valley coherence is easier to maintain with respect to the circular polarization. I'll come back to that later. In general, they are fairly bad. So the question is, why is it so difficult to observe highly polarized emissions from these material systems? So there are two aspects of this. So first of all, like I said, you must generate good states, meaning highly polarized states. So let's look into that, how we normally do it. So when we normally do a photoluminescence measurement, so we excite at a very, let's say at a high energy state. So either in an excitonic state, or if you are significantly off resonant, then you can actually create this electron hole pair separately, right? So now, as Ashish mentioned, that there are different states that are possible. So this is like, let's say you are, in this particular figure, let's say you are generating through your light some NS state. Okay, and could be anything beyond 1. So now, so they will gradually relax to your 1s band, but that is not sufficient for them to emit light. So they have to eventually come down to a very narrow region of the K space, which is known as the light cone. Because as you know, because of momentum conservation, and the photon has a very small momentum, so you really have to come down to a very, very narrow regime. Okay, and while this happens, and this usually happens through phonons, so you lose the coherence or the polarization information. right? So here there's one experimental data that we have on MOS2. So we are, I'm sorry, this is for WS2. So here we are just, coming down in the excitation closer to one state, and you see your observed DOLP, or the valley coherence, is actually improving because you're losing less information or less randomization of the information due to this kind of phonon scattering. Okay. So it's very important that we sort of excite as close as possible to this one state. And typically in literature, people try to follow that. Otherwise, it's very difficult to do this kind of experiments. Okay, but then there are a couple of other ways of generating these high-energy states, and this is something we'll use in this talk. So the first one is, let's say you excite in a particular state, let's say a 2s state. So then it's possible for a transition from 2s to 2p and 2p to 1s directly without the phonons. And because of this resonance, it can be a very fast and efficient transfer. The advantage of this is that you don't lose the polarization information, right? So this is some sort of an optical transition that's happening, maintaining the selection rule. There's another possibility, which if time permits, I'll show later. So is through a phonon absorption, phonon scattering only, but through a single phonon scattering. So we can actually, using a tunable laser, we can sort of excite in certain, let's say some nth state, and then we choose that such that there's a resonance between this state to this state through a given phonon mode. So, and if we choose this phonon mode to be polarization maintaining, like A1G, we know is a polarization maintaining mode because of the Raman tensor is diagonal. You can actually maintain the polarization information. Okay, so here this is going to be the predominant one because of resonance again. The other off resonant slow processes would not be dominating. All right. So we'll see how we'll use this later, but let's talk about the another difficult task, which is, let's say you generate a good state, but the question is for how long you can maintain this polarization. So what's the primary mechanism for this sort of valley decoherence or valley depolarization? So this is a well-known MSS Silver-Sam mechanism, which was proposed several years ago. So where you actually have an inter-valley exchange interaction, and that sort of creates the sort of perturbs this Hamiltonian. And so there is a time evolution of the density matrix, which eventually, after a few algebraic steps, you can find out how the pseudospin evolves over time. Okay, so which has a omega cross S state, which basically comes from the precession of this kind of pseudo-magnetic field. And also there is a scattering term. Please note that if you don't have this term, so only the scattering term, it does not degrade any polarization, right? Because this is sort of diagonal. And then, of course, there's a lifetime term, and this is the generation matrix. So to explain this equation pictorially, so let's say, you are generating some linearly polarized light at t equal to 0. So like I said here, this cross product is actually 0. So nothing really happens. But then it scatters because of this finite scattering rate. And it scatters to some other point in the light cone. So once that happens, now in the cross product, this term is not 0. And so what happens, it starts precessing around this vector, right? So, and this keeps on happening. It scatters and precesses and keeps on happening until at some point of time where the exciton recombines and it sort of radiates the light. So at that point, whichever direction the pseudospin vector is pointing to, you measure in your experimental data the corresponding polarization, right? So now, So this is what is happening. So your exciton is here, and it sort of scatters and precesses, and eventually along this direction you are measuring this thing. So now the question is, how can you improve this situation? So the first thing that you can do is you can screen through an environmental engineering. So let's say what we do in this work is encapsulate with graphene. So because of that screening, what happens is that the electron and hole, they are sort of separated apart. And so there is a less wave function overlap between the electron and hole. And so the exchange interaction goes down. And because the exchange interaction is going down, you should expect that this kind of precision is happening at a slower rate, and you improve your valley coherence. However, one drawback is that because the electron and hole are separating apart, the lifetime is also going to increase, because the oscillator strength is going to go down. So if you can do something such that this lifetime can be suppressed. So here, for example, we use a graphene transfer, and so the net lifetime is suppressed. So then you can actually cut down on lifetime, as well as you are sort of separated apart. So the reduced electron hole overlap is going to improve your valley coherence. So this is the approach that we take in this work. So these are the experimental data. So first we have an HBN encapsulated molybdenum disulfide flake, where we achieve 37% valley coherence. So here we are exciting close to the 2s state. Okay, so we don't degrade the polarization because of the scattering from the higher energy states. Not much on the HBN encapsulator one, but later I'll show that. So the next step that we have is HBN encapsulated MOS2, but then the entire thing is encapsulated by two graphene layers. So here you see it's not really improved much, it's still about 40%. The reason is that although it's screening because of graphene, but the lifetime has also increased. So both are sort of canceling each other. So the next step we had is like one-sided graphene, and there we see a significant enhancement, about 79.6%. And then finally, we had a graphene encapsulated MOS2, where we got exactly 100% polarization. So this was really great to observe for the first time, that you can achieve a perfect valley coherence from this kind of highly exchange dominated stacks. So to analyze this situation further, so what we did is, okay, so before that we measured the circular polarization as well, and you see that we observed in the same stack, graphene encapsulated MOS2, circular polarization was not 100%, but about 81%. And the reason is that, because the pseudomagnetic field is in plane, it's easier to maintain the valley coherence. There's a linearly polarized light. However, because your pseudospin is also sort of in the same plane. However, in the circular polarization case, the pseudospin is pointing toward this, so you have a strong component for the first term, and that degrades circular polarization more rapidly. Okay, all right. So anyway, so we wanted to understand this further. So what we did is so exactly how this screening versus lifetime that's playing a role. So in the HBN encapsulated MOS2, what happened is that, so we measured the 2s state and 1s state separation, and we find it's about 144 millielectron volt. And then we solved the Bethe-Salpeter equation and found out the total binding energy of the stack is about 379 MV. Okay. And we also did corresponding the TRPL, time resolved photoluminescence measurement. So we found it about like 3.6 picoseconds. Okay. So now we did the same thing on the graphene and HBN encapsulated stack. We found out that the 2s to 1s separation came down to about 63 millielectron volt. So our Bethe-Salpeter equation predicted that the corresponding binding energy is about 162 millielectron volt. So see, the binding energy is actually going down very significantly, which means the electron and hole are being separated apart in physically in the real space. Okay, and also you notice that the lifetime has increased, and that also makes sense because your oscillator strength is going down, right? And thirdly, in our graphene encapsulated MOS2 stack, we found a very short, like 43 millielectron volts per second between the 2s and 1s state. And the corresponding binding energy was about 122 millielectron volts. So you really push the electron and hole apart. However, the lifetime did not degrade because there's a strong non-radiative loss directly to graphene. So you're truncating the lifetime, as well as you are sort of pulled electron hole apart, so cut down the exchange interaction. Okay? And that's how we believe that we have achieved this 100% polarization. So this is also repeated on a different case, the tungsten sulfide. So graphene encapsulated tungsten sulfide. Again, we achieved 100% polarization, and we also did a polarization dependent TRPL measurements, which sort of shows that the excitons are really remaining 100% valley coherent in their entire lifetime. So that's really interesting to achieve, because now it becomes available for many quantum related applications. So, and of course this so yeah, all right. So the other thing is we sort of simulated this equation and plotted the degree of linear polarization as a function of, let's say, the scattering rate. So what we interestingly found is that it sort of comes down initially and then it goes up. This coming down part is pretty obvious, that your scattering rate is going down, so your improvement in the polarization, but it sort of bounces back again. And this is because of an effect what is known as motional narrowing, which is derived from this NMR literature. So where basically because of very fast scattering rate, there is a random phase cancellation that happens in a 1D random walk, and it actually improve on the valley coherence numbers. Okay, so this is the GMG stack, and this is the this is the HMH stack, the HBN encapsulated MOS2, and this is the graphene encapsulated MOS2. So it very nice correlation between our simulated numbers and the experimental data. Okay, so later we verified this from some Monte Carlo simulation as well, which I'm not showing now.
So Kaushik, you have 4 minutes of talk time.
Sure, thank you. So, so in the last 4 minutes, then I'll just quickly talk about the other relaxation mechanism that I talked about, where through a phonon you are sort of relaxing the excited states to the one state. Okay, and see what are the implications it may have. So, so quickly speaking, so typically all these monolayer TMDs, because they're so thin, you have to put it on some substrate. So the luminescence or absorbance, whatever, everything is sort of bottlenecked by the inhomogeneous line width broadening. So if you have a potential fluctuation on the substrate, it sort of transfers easily, and you basically get something like this, while the true line width should be something like this. Okay. So the question is, what can we do to achieve this kind of, the true line width in these material systems? So what we did is that we had a tunable excitation, and we were measuring the detection in a spectrometer. So you can see, as we change the excitation wavelength, sort of from a broad line width, it suddenly comes down to a narrow, and this is normalized, so it's not very obvious here, but you can see from here. So this is about 120 in intensity, and here the intensity is 30,000, right? So there's about 300 times enhancement in the intensity, plus it became very, very narrow. So what's really happening here is that usually in this case, as I mentioned earlier, we are relaxing through these multi-phonon states, while in this particular case, it actually resonates with the A1G phonon, and through a single shot, it comes down here and it gives you a very high luminescence and a very, very narrow line width. The line width part, why it narrows down, is a big story, and I don't have the time to explain that, but basically what happens is that you are actually resonating between those spots which are actually matching your excitation and luminescence, this separation. So you're basically picking up only those spots, and that's there's this very strong energy space correlation that happens. And you can actually see that, this is the off resonant excitation, and this is the tunable, resonant excitations. So you can see that, you are actually able to make what was predicted 5 years or 6 years back experimentally in this data. Okay. And finally, it also, the line width that we achieved is about 1.5 millielectron volt, which is a record low number, whatever is reported to date in this literature. And please note that in that 1.5 millielectron volt, our laser itself was 1.2 MeV because of it was passed through a monochromator. So if we deconvolute that, then the actual line width that comes out is 0.23 millielectron volt, which sort of matches well with the reported 1 to 2 picosecond numbers for the lifetime. So we are really, going towards the true homogeneous line width in this system. And finally, this is also a highly polarized system. The polarization is maintained very nicely. We get, this is not exact 100%. We got something like, 90% polarization from this, from the stack. So that's all I have. So I wanted to just conclude saying that, this ultra narrow line width and perfect polarization is really possible from these monolayer semiconductors, which earlier we should think that it's really not possible. And so this really, a good step towards manipulating Valley as a quantum state. Yeah, thank you.
So thank you, Kaushik, for an excellent talk. Once again, 100% polarization, Valley coherence achieved. So very good. So the talk is open for discussions, questions. Devjani, I see.
Yeah, Kaushik, very nice talk. So
thank you.
I want 2 comments from you. One of them is that that for achieving this 100% Valley polarization, what can be the role of these vacancy mediated states and also interlayer exciton? So first I wanted to know that if there is a vacancy mediated state, like for some of these TMDC samples, we have seen that mid-gap states are extremely well localized, like a straight line. So if those can be utilized as a trapping states, then definitely the exciton lifetime can be increased. But does it have any impact on Valley polarization? So that is my first question. And then the next is that there are interlayer excitons like these MOS to WS2 kind of samples. So does it also have any impact on Valley polarization? So these are the 2 things.
Right. So for the first part, so I guess you are talking about trapped states, right? So yeah, one of the advantages of trapped states is that, the scattering mechanism is slightly different. And I believe that because it's quantum confined, so the scattering is going to be suppressed, right? So, so I assume that, so there's a second part of that also, that how much Valley nature these trapped states are going to retain. Meaning that, these trapped states, it doesn't have to come from the K or K prime valleys, right? It can be anywhere in the entire below zone, right? So, but there are, of course, certain states where, we do funnel these K excitons into sort of a strained trapped states close to the K value. So for those cases, I think it is possible. In fact, we have some recent data on modest super lattices which show very high polarization, not 100%, but very high polarization. But I cannot comment on those states which are, let's say, somewhere which are arising from somewhere else in the below zone, because they have nothing to do with the K or K prime valley. And so accordingly, you don't know whether it's going to have the right symmetries for these emissions, right?
Yeah, it will depend upon the value that whether the trap, that whatever the trap states will retain the K or K prime valley nature.
Yes, so for those cases, I think it is good, because the scattering rate is going to be less because of the quantum confined nature of these states. That's what my preliminary guess is, but I think we can discuss on this later. Yeah. Sorry, what was the other point?
Other thing was that interlayer exciton. Yeah.
Right. So interlayer excitons are significantly slow. Like it can come, depending on how well matched let's say you have the same chalcogen, then they are sort of well matched. But if you have different chalcogens, the lattice matches are different. That's one thing. Secondly, there could be a twist angle, right? So depending on these
that will actually destroy the value. That may destroy them.
Right. So what happens is that, so at least what we see in our lab, that the lifetime of these interlayer excitons are significantly larger, like in the order of, let's say, nanoseconds to hundreds of nanoseconds, right? So they have many things to do in that hundreds of nanoseconds, right? It's fairly uncontrolled. So my guess is that, like I showed in the data, that it might be a little difficult to maintain polarization because of this. But having said that, I must also say that because the electron and hole are residing in two different layers, their overlap is relatively less. So your exchange is going to be less. So I think we can just so we have to just do it and see probably.
Yeah. Okay. Thank you. Nice talk.
Yeah. So one quick question from Ashish.
Hi, Kaushik. This was an excellent talk. Thanks. I'm just curious, is this contribution to broadening through by scattering through other states, is it homogeneous or inhomogeneous?
So can you please come again?
Yeah, this contribution to the line width broadening when the electron scatters through various states to the ground state, is it homogeneous or inhomogeneous?
Right. So it turns out that that sort of exaggerates the inhomogeneous line width. So basically, what happens is that since you have many states that are coming, so when you see one state, if I go back to let's say this cartoon diagram, so you can think about it as you have several one states which are spatially localized at different points under your laser spot, right? Now, if it is coming through multiple phonons, you end up exciting all of them. And that's where the problem is. So you, while emitting, everything emits, and you basically get a broad spectrum. On the other hand, if you come through a single phonon narrow resonance, then what you are doing really, let's say you're exciting somewhere here, and it resonates exactly with this. So nowhere else, these things, come into picture. So you're not relaxing to these states. You're only relaxing to this. And because of that, singularity due to this resonance, only this state is sort of, sees all the oscillator strength. And that's what we see.
Small comment here, don't you see phonon bottlenecks in these kind of materials? Those are very common, right? So much narrowing down that phonons, will it be possible? Because in this kind of 2D TMDC systems, phonon bottleneck is a very common.
No, so we still have, so this is a phonon emission, right? You can always do phonon emission. This is not an absorption. So you are coming at a higher energy, and it can always emit even if you are at low temperature. That's not a problem, right? And it can come down to so this kind of states. So we never see any such feature here. However, for the absorption part, yes. I mean, we do expect some bottlenecks like that, but not in the emission.
Not in emission. Okay.
Yeah, I have to cut down the discussion here. So let's thank Kaushik once again for an excellent talk and move on. So we have Suvodeep. Are you there?
Yeah. Am I audible?
Yeah, you're audible. So the next talk is by Suvodeep Paul from IISER Bhopal, and he'll be talking about electron-phonon coupling in the semiconducting and topological semimetallic phases of MOX2, sulfur or tellurium. So over to you, Suvodeep. So I'll give you a warning at around 12 minutes.
Yeah, sure. Thank you.
Start sharing your screen, please. Yeah.
Are the slides visible now?
Yeah, just go to full screen. Yeah, perfect.
Okay. Thank you. So, hello and good afternoon to everyone. I am Suvodeep, a PhD student from the Department of Physics at IISER Bhopal. I'm working under the supervision of Dr. Surajit Saha, and today I'll be presenting some of our recently published works. The topic is electron-phonon coupling in semiconducting and topological semimetallic phases of MX2, X being sulfur and tellurium. So basically, this class of materials represented by the formula MX2, they're called transition metal dichalcogenides, and they are essentially 2D layered materials that can be exfoliated into atomically thin flakes. And depending upon their atomic arrangements, they can be classified into a variety of phases. For example, the 2H phase here has a trigonal prismatic structure, while the 1T phase has an orthogonal structure and octahedral structure, and the 1T prime is a distorted octahedral. Now, by breaking the inversion symmetry of the 1T prime structure, we may obtain the TD phase over here. Now, interestingly, all of these different phases also exhibit different properties. For example, the 2H phase exhibits a semiconducting band structure, which is also very thickness dependent. And as a result of this semiconducting nature, it has a plethora of different semiconducting applications, ranging from sensor applications to electronics and optoelectronics, then which are enlisted here in this review article. Then we have the 1P prime phase, which again has a band inversion in the band structure, and it's also characterized by a very small band gap opening. And this is essentially a quantum spin Hall insulator, and such materials have been proposed to be used in topological FETs. The third phase we will be talking about is the TT phase, which has linear dispersion about the band around the band touching points called Weil points. And this is essentially a type 2 Weil semimetal. And we know that type 2 Weil semimetals, for example, the TdWt2 has recently been demonstrated to show charge to spin conversion, which is why it has very good applications in spintronics. So keeping in mind some of these applications, we've done some phononic studies of different phases that I'll be just elaborating in the next slides. So first of all, here we see a lattice vibration, which may be represented by a bosonic hypothetical particle called phonon, and ideally they're considered to be harmonic. And under the harmonic approximation, this is the harmonic equation that we generally represent it with. And under this approximation, we considered the phonons to not interact with each other, and they are ideally dispersionless in energy and have infinite lifetime. But in a more realistic scenario, we consider the anharmonic approximation, where the interaction of phonons with other phonons is allowed, and therefore they have a finite lifetime. So essentially what happens is the optical phonons decay into acoustical phonons, and this theory is manifested as a temperature dependence of the frequency and line width, which are shown by these equations, which are also shown by these curves. So importantly, what we see is that when the temperature is not too high, we may approximate these curves to be linear in temperature, with a negative slope for frequency and a positive slope for the phonon line width. So further, if we allow the interaction of the lattice with electronic charges, this GIF shows some sort of interaction of that sort. What happens is we see a local distortion that travels or propagates through the crystal, and this sort of interactions give rise to a lot of exciting phenomena, including superconductivity. And as can be quite easily imagined, that this would also change the phonon eigenstates, and that therefore these interactions might be manifested as a deviation from the anharmonic trends that we just discussed. So this is the frequency and line width of the phonon as expected from anharmonic behavior, and this deviation that we see represented by the dotted lines is what would happen under the influence of electron-phonon coupling. So in our study on 1T prime MOT2, so this is the Raman spectrum of 1T prime MOT2, we saw that this phonon P1 here, it shows a clear signature of electron-phonon coupling. And that is manifested by an anomalous temperature dependence of the mode frequency and also the line width with respect to the anharmonic behavior shown in the insets. And we could also see the evolution of the electron-phonon coupling strength from the slopes of these anomalous curves. And that goes like this, that when we thin down the 1T prime MOT2, we saw an increase in the electron-phonon coupling. This is essentially because of the increase in electron doping with thinning down of the sample, which has been also reported by other studies. And then we see a suppression of electron-phonon coupling for the thin layers. And finally, for the monolayer, we see a complete suppression. This is also consistent with the fact that the very thin layers of layer of TMDs, they get very strongly hole doped when they are exposed to the atmospheric air and moisture, for example. However, in our study on the rhenium doped samples, which are rich in electrons, we see that the suppression of electron-phonon coupling is not strong enough. And from these observations, we could kind of infer that electron-phonon coupling strength in this system could be tuned by charge doping. So we went on to see the effect of this charge doping on the topological phase transition as well. So basically the TD MOT2 and the 1T prime MOT2 are the two topological phases, this being wild semimetallic and this being quantum spin Hall, as we discussed in our first slide. And as we also discussed that the 1T prime MOT2 has an inversion symmetry, which is broken in the TD phase. And this breaking of inversion symmetry is manifested by the appearance of a new mode in the TD phase, which is not seen in the 1T prime phase. So basically this phase transition may be seen through Raman as a hysteretic phononic properties, like as a change in hysteretic change in phononic properties around the phase transition temperature, which appears at around 260 kelvins. So interestingly, what we see here is that for the very thin layers, if we recall from the previous slide that the thin layers were hole doped, we see that the thin layers do not undergo a transition to the TD phase even at low temperature, which is to say that the hole doped samples are stabilized in the 1T prime phase. Now we see that on electron doping these very thin flakes, by exposing them to ammonia vapor, we get back the TD phase. So this tells us that electron doping can again stabilize the TD phase. Further, when we continue our studies with the rhenium doped sample, which is again rich in electrons, we see the TD phase to appear at low temperatures. So this kind of proves that we can interchangeably stabilize either of the two phases by proper electron or hole doping. And further details of this work can be found in this paper. So we went on to study the 2H phase again of MOS2 and MOT2. We've performed experiments with different lasers to probe the first order and as well as the second and higher order phonons, mainly to probe the phonons at the Brillouin zone and also away from the Brillouin zone. And we performed temperature dependent experiments, which gave us some sort of data which looks like this. So all of the modes we see show a red shift as a function of temperature, which is what we had, what we would expect from the anharmonic theory. And on the other hand, the line widths show an increase with increase in temperature. That's also consistent with the anharmonic theory. Now what we would be interested in is to see the strength of the anharmonicity and its dependence on various parameters. So first, we would see the effect of temperature on the frequencies, on the phonon frequencies. So as we saw that the phonon frequencies show redshift with temperature. So this is the linear equation we fit it with, and we obtain the negative slopes of the curves which give us the strength of the anharmonicity. We see that the strength of anharmonicity has intricate dependence on two factors. The one is mode symmetry. So if we consider a particular thickness, then for a particular thickness, we see, depending on the different phonon symmetries, we get to see different extents of anharmonicity. For example, the A1G mode for both MOS2 and MOT2 shows a stronger anharmonic behavior compared to the E2G modes here, which are in-plane modes. And another dependence is that for a particular symmetry, for example, the A1G, we see that an increase in the number of layers decreases the anharmonic trend. The suppression may be accounted to the increase in interlayer interactions with the increasing number of layers. And basically, because A1G mode is the out-of-plane mode, we see a more strong suppression rather than the E2G mode, which is an in-plane mode. However, there may be role played by electron-phonon coupling as well, which we'll be discussing in the next slides. So now,
what if we have 2 minutes of talk time?
Yeah, sure. I will finish by then. So now we would discuss about the line width here. So the line width, as we had already seen, also shows an increase with temperature, and these are the linear equations with which we fit them. And the psi values again give us the slope and therefore the strength of anharmonicity. And we must remember that the line width of a mode basically constitutes contributions from anharmonicity as well as electron-phonon coupling. So basically in this GIF, we see that this green solid line represents the anharmonic line width trend, and the EPC is represented by this dotted line. We clearly see that by tuning the strength of the electron-phonon coupling, or rather increasing it, we can basically decrease the effective anharmonic behavior. So the fact that with an increase in thickness, we see a decrease in anharmonic strength may be accounted to the fact that with an increase in thickness, we see an increase in electron-phonon coupling. So further, we have further proof of this. So we could probe using resonant Raman, we could probe this omega-2 mode. So this is a second order mode, which we had to probe with the 633 nanometer laser. And this mode has been previously reported to be associated with electron-phonon coupling. And as expected, we see an anomalous behavior in the evolution of the line width as a function of temperature. So it decreases with increasing temperature. And this anomaly is expected for electron-phonon coupled modes. And what is also interesting is that this anomalous decrease in line width is seen for all the different thicknesses of MOS2 that we studied. And we also see that the anomaly increases as a function of thickness. So this again kind of proves that with an increase in flake thickness, we get to see an increase in electron-phonon coupling, therefore confirming our previous assumption in the last slide. So further details of this work may be found in this paper. So with that, I'll come to my concluding remarks. So mainly, we have studied the 1T prime phase, which shows a topological phase transition and electron-phonon coupling, both of which could be tuned by charge doping. The other study that we performed was on 2H phase of MOS2 and MOT2, and we saw the anharmonic behavior to be dependent on flake thickness and phonon symmetries, and electron-phonon coupling also played an important role in the understanding of these behaviors. So with that, I come to the end. I would thank my supervisor, Dr. Suvodeep Saha, for his guidance, my entire lab at IISER Bhopal, and then particularly Dr. R.P. Singh and Mansi Mandal from IISER Bhopal for the synthesis of the 1T prime MOT2 and rhenium doped MOT2 crystals. Finally, thank the organizers of the QMAT conference for allowing me to speak here. I thank the audience for their attention. I'm open to some questions if anyone wants to ask.
Thank you, Suvodeep. So we'll have one very quick question. So Devjani.
Yeah, Suvodeep, regarding 1T prime phase of MOT2. Now, whenever you after 120 Kelvin, there should be a transition from a monoclinic to orthorhombic phase from 1T prime to TD, right?
It happens around 250 Kelvin.
250 for such a high temperature. Okay, actually, there is a paper which actually reports this 1T prime MOT2 superconducting
Yeah,
thing.
yeah.
They are telling that the temperature is 120. Anyway, it doesn't matter.
So,
But
ma'am, actually, I would clarify a bit. So, basically, for bulk, it's at 250 Kelvin, but it has a thickness dependence for the temperature of the phase transition.
Okay.
So, for a thinner flake, we expect at lower temperatures. Yeah.
Oh. And I just wanted to know that whenever you are going to the TD prime phase, do you have any signature of this negative phonon, or is there any signature of kind of structural instability in the system? Because I am doing calculation presently on this system. That's why I'm asking to the experimentalists.
So, as for the experiments that we have performed, we never saw anything of that sort. But the only thing is that we saw that this TD phase, basically the transition, it has also been reported by other people. For thinner flakes, it becomes a bit tricky. So sometimes we see it stabilizing in one of the two phases. And it sometimes it happens that we do not how to say it. So it becomes difficult to predict as to which way it would go.
Which phase it is, but there may be phase mixing also, right?
It happens that phase mixing is there. Even
when you dope rhenium, what is happening? Which phase stabilizes? Orthorhombic or monoclinic?
Basically, both of them exists, but then the phase transition temperature is tuned a bit by rhenium doping. And actually, rhenium doping, there are studies on the theoretical study as well. So that predicts that the electron population in the system increases with rhenium doping. So that's a way.
Depends on which phase you are, whether you are orthorhombic or whether you are.
Yeah, particularly in the TD state, which is the low temperature phase. So that happens. And in general,
and your electron-phonon coupling increasing? Is it increasing with
electron-phonon coupling, ma'am? It shows a fairly consistent behavior throughout both the phases. So if you see this, I think I have it. So basically, if you look at this image, so this is where the phase transition takes place. But more or less, we can say that the behavior of the anomaly, which is basically a signature of the electron-phonon coupling, that is fairly consistent below and above the phase transition. So it's difficult to comment whether the electron-phonon coupling increases with the change in phase. At least from the
I'll have to cut short the discussion. I'm sorry about this.
Thank you so much. It's a very nice talk.
Yeah, nice, Suvodeep.
Thank you. Thank you.
Yeah. So we'll move on to the last talk of this session. So let me invite Shalini Badola from IISER Bhopal, and she'll be talking about competing many-body effects in tellurium-based hexagonal perovskites, a Raman spectroscopic study. So Shalini, are you there?
Yes, ma'am. Am I audible?
Yeah. So
okay.
Could you start sharing your screen?
Yes, ma'am. So is screen visible?
Yeah, so go ahead.
Okay. So hello everyone. This is Shalini Badola, PhD student at Department of Physics, IISER Bhopal. I'm working under the supervision of Dr. Surajit Saha in light scattering group. Today, I'll be presenting my work on competing many-body effects in tellurium-based hexagonal perovskites. So material science has been of immense importance in revolutionizing the human civilization. As pointed out by Nicholas Spalding, we have tremendously evolved from Stone Age and right now living in Silicon Age, where the fundamental property of charge is being harnessed for device application. Now, if beside charge, if we can involve other degrees of freedom such as spin, lattice or orbital, then we can really advance in terms of data storage and fast information transportation. Now, this can be achieved by generating materials which show coupled degrees of freedom or multiple ferroic attributes, which are known as multiferroic materials. So the coupling between the fundamental degrees of freedom, which are spin, lattice, charge, and orbital, can be of importance in context of multiferroics because they generate competing many-body effect, which can lead to novel phenomena like magnetoelectricity, superconductivity, or resistivity. So the coupling among these degrees of freedom have comparable energy scales. So any external perturbation to the system under investigation can play a decisive role in determining their ground state. Particularly if we consider lattice or phonon degree of freedom, then any change or distortion in the lattice can modulate the electronic, magnetic, and orbital dynamics, and therefore it can be really important to, exploring them can be really important to get fundamental insights as well as potential applications. So in today's talk, I'll be mostly discussing about these coupling effects in perovskite materials. Now, one efficient way to explore or understand these coupling effects is Raman spectroscopy, which primarily probes the phonon response to external perturbations like temperature, pressure, magnetic field, electric field. Phonons are quanta of lattice vibrations, which are basically determined the parameters such as frequency, line width, and area. So if we consider temperature as the external perturbation, so the temperature dependence of the phonon frequency is generally given by this equation, which carries the contribution from phonon-phonon, spin-phonon, and electron-phonon terms. So when the contributions from this phonon-phonon, spin-phonon, and electron-phonon terms are negligible or small, then the temperature dependence of phonon follows the behavior like represented by this schematic. That is, as temperature increases, the phonon frequency should decrease. This behavior is known as normal behavior, and deviation from this behavior is termed as anomalous. So now suppose if we consider any system which is not carrying spin-phonon coupling or in an electron-phonon coupling. So basically spin-phonon coupling is present in magnetic materials. Electron-phonon coupling is usually found in semiconducting materials or materials which can provide charge carriers to couple with phonon. And phonon-phonon interaction can appear in materials which near the structural transition or in the materials which exhibit negative thermal expansion. So the manifestation of phonon-phonon interaction in Raman spectroscopy can be seen in this way, that is represented by this first schematic, where as we increase the temperature, the phonon frequency also increases, which is contrary to what is expected from the normal behavior. Similarly, coming to spin-phonon coupling part. So if the phonon, for a material which exhibits when there is a magnetic transition, so if phonon coupled to that, if phonon can respond to the magnetic transition, then we can say there is a presence of spin-phonon coupling in that system. Similarly, electron-phonon coupling, as discussed by Suvodeep in the previous talk, it can also manifest in the form of this anomalous behavior, or in terms of this second one also. An additional feature can be the presence of this Pano line shape. So in general, the line shape of a phonon is Lorentzian, and if the charge carriers can couple to electronic charge carriers can couple to phonon, then in that case, the line shape modifies and it can lead to this Pano asymmetry. So these manifestations can be studied or generally found in perovskite oxides with general formula AbO3, where A is usually a divalent cation and B is a transition metal ion. As we introduce additional cation at the B side, double perovskites of the form A2BB-O6 get stabilized, which may take various structures depending upon the size of A or B side cation and their corresponding valences. The phase stability of these materials is decided by this empirical relation, which is given by tolerance factor, which is ideally unity for a cubic material. For tolerance factor greater than 1, hexagonal perovskites get stabilized, which comprises of phase shared or S-shared octahedras with a reduced metal-metal distances along these trimer, phase shared or S-shared trimers. Now, this reduced metal-metal distance can be of importance because they can modify the electronic and magnetic property of a material, which can help us in generating new quantum materials. So Ba2Zn-TeO6 and Ba2Ni-TeO6 are two such materials which crystallizes into hexagonal structures under ambient conditions. So for the sake of convenience, I would refer them zinc system as BZT now onwards and nickel system as BNT. So BZT, it undergoes a structural phase transition from high temperature trigonal to low temperature monoclinic phase below 150 Kelvin. While BNT, it exhibits an antiferromagnetic transition below 8.6 Kelvin along with a strong magnetic frustration. One interesting point to note here is that despite being isostructural to BZT, it does not show any structural phase transition. So this raises the question that what makes the structural dynamics of nickel or BNT different from BZT so that it doesn't undergo a structural phase transition. So to address the same, we have carried out temperature dependent Raman spectroscopy on BZT, where we found that most of the phonons split below the phase transition, that is below 150 Kelvin. Particularly if we look at this lowest frequency phonon mode, that is Z1, it first exhibits an anomalous behavior upon cooling, and below 150 Kelvin, it shows normal behavior. An interesting point to note here is that the overall change in frequency of this mode in the high temperature phase, that is trigonal phase, and as well as in the low temperature phase is really large. It is around 120% in the high temperature phase, which is significantly high as compared to commonly encountered enharmonicity of 1.1 to 2%. In the low temperature phase, it is around 94%. So from this, we can say that the enormous enharmonicity associated to this soft mode can play a very important role in driving the phase transition in BZT. And therefore, we also carried out temperature dependent Raman measurements on BNT, that is Ba2Ni-TeO6, where we found that the lowest frequency phonon mode, that is N1, and so from this figure we can see these are basically the room temperature Raman spectra of these two systems, where we see that the phonon modes mostly matches at the room temperature. So we will now focus on the lowest frequency phonon mode because that is what is driving the phase transition in BZT. So the lowest frequency phonon mode splits in case of BZT, while it does not split in case of BNT down to 80 Kelvin. So this suggests
Shalini, you've got 2 minutes. Huh?
Okay. So this suggests that this N1 is not a soft mode, which is driving the phase transition in case of BZT. And therefore, we can conclude that this gives one of the, this is why, okay, so to compare the enharmonicity, we have estimated the enharmonicity in case of nickel, which is around 41%. So this, if we compare with the zinc system, it is around 120%, but so it is 3 times lesser than the zinc system. So this gives an indication why there is absence of phase transition in case of BNT. But let us recall that there is a strong enharmonicity, strong magnetic frustration in case of nickel system. And a strong magnetic frustration should promote a structural transition or lattice distortion in the lattice. So therefore, to understand the same, we further carried the Raman measurement down in the magnetically ordered phase, where we found that most of the phonon modes deviate from the general cubic and harmonic behavior below 100 Kelvin. When we measured the magnetic data, we found that the inverse susceptibility also shows a deviation from the linear trend right around the same temperature. This gave us an indication that there is a coupling between spin and phonon degrees of freedom. Also, the spin-phonon coupling is sort of relieving the magnetic frustration in the system, which is also helping in prohibiting the structural phase transition in BNT. Therefore, from this talk, we can conclude that in case of BNT, the interplay between large harmonicity, spin-phonon coupling, and magnetic frustration is playing an important role in prohibiting a structural phase transition in nickel system. Thank you for your attention and providing me opportunity to present my work here.
So thank you, Shalini, for a very nice open for any questions. So I don't see any questions. So just could you go back to your previous slide?
Yes.
Yeah, so here what I see is that some of the modes, the fitting is quite good compared to the rest. Do you have an explanation for that? For example, the N5 or the N16 one?
Okay, ma'am. So N5, okay, so you mean this red curve.
Yeah.
So actually what is happening, this red curve is what the phonon is expected to follow.
Yeah.
So what is happening below 100 Kelvin, these data points are deviating from this expected trend.
No, that's what I can see that, but N5 and N16 are deviating less as compared to say N3, for example, or N2, okay, for example. Do we have some understanding on that?
Okay, ma'am. So actually, so at on the higher temperature sides, we don't have that many data points. Like if we can go further, so I mean, if we could take for more data points, then it would have been better to show.
Okay. Okay. Thank you. Any more questions? If not, so let's thank Shalini once again. So let me take this opportunity to thank all the speakers of this session. So we had a wonderful session with very new and novel results. So thank you all. Over to Pratap.
Hi, so thank you for chairing this session, and thank you all the speakers for a fantastic presentation and for keeping to the time. We have now a poster session, so I would request everyone to maybe have a quick tea and join the poster session. There will be presenters waiting there. So we come to the end of today and see you again in the poster session and then tomorrow for the oral.